All right, so today we're going to go through the remainder of Chapter 5, the Patterns chapter. So last time we looked at three significant patterns: the strategy pattern, the composite pattern, and the decorator pattern. So those are definitely important. And today I want to do two things. I want to go through the section on how to recognize patterns, and then one longish example that shows a whole bunch of patterns at work. So it's a common question whether some particular setup is actually an example of a design pattern. And there's the first thing is that when you look at patterns, you always want to look at the intent of the pattern, because patterns can look very similar. Think, for example, about the composite pattern and the decorator pattern. When you look at those UML diagrams, here's the one of the decorator pattern, where you have the decorator class that both has and is a component, and then you have the composite pattern over here, where you have the composite that both has and is, well, a primitive, except you'd have to look very carefully to see that there is an asterisk over here than a 1. So looking at these UML diagrams is probably not the best way to having a first step to see whether a pattern applies. But the intent of decorator and the intent of composite is quite different. I mean, in composite, you definitely have this notion that you're collecting a whole bunch of similar things. Whereas with decorator, you're changing the nature of a single thing. And so if you think of that, you're unlikely to confuse the two. But that's not good enough, because then you run into the trap that you look at a pattern, and someone asks you, is this a strategy pattern? And it's very, very common then just for people to think, well, is it strategic? And if it seems, and then they say, what's it even mean? Is it strategic? And then people even say, well, that sounds useful. And they say, well, it must be the strategy pattern. But that's, of course, not right. Not everything that's useful or strategic is an example of the strategy pattern. And so when you look at the abstract description of the strategy pattern, and it talks about a class can benefit from different variants for an algorithm. Clients sometimes want to replace standard algorithms with custom versions. That is in a short amount of time. That is very difficult to see. Does that really apply to a situation or not? It seems like super abstract. And so that's why I always recommend is that for each of the patterns, you think of a specific example and kind of use that as guidance. So what's an example of the strategy pattern? Excellent. Layout managers. So if I've gotten you to the point where whenever you think strategy pattern, you think layout managers. And maybe even think layout managers or comparators. Then you have some examples, and it's much, much easier to be guided by those examples than being guided by this very nebulous and general thing where it says the class can benefit from variants of an algorithm. So that's my recommendation. So that with each pattern, that you think of an example of where it occurs in the wild. Composite. So what's the poster child for composite?
The elements inside of elements.
Yes, the elements inside the components inside the container, as it's said in swing speak. Okay, so components and containers are the poster child for composite.
Arrays
Yeah.
composite.
What's that?
Arrays are they composite?
Arrays?
Yes.
Okay, now that's a good question. So you're saying are arrays composite? And so let's see. So arrays of what?
Arrays of arrays.
So the question is an array of arrays an array? And so I guess in that sense you could theoretically do that, except that it doesn't work in a strongly typed language like Java. Because in Java you can't just say arrays, it has to be an array of what. So in Java arrays wouldn't work out because if you think of specific types, let's say array of integers, and now you have a whole bunch of those, then you can't put them in an array of integers. You have to put them into...
I mean, like, if you have like a two-dimensional array, right? That's an array of arrays. And then inside of the elements could be like integers.
Okay.
Or could be strings.
Okay, so if you have like an array of anything, like then you can make that work, because and so in Java it's tough. And I'll give a bit of code in just a minute. There are other languages like in JavaScript or Python where you don't worry about types, and you can have heterogeneous arrays. You can toss a string and a number and an array into an array. And at that point, yes, an array is a perfectly good example. So a heterogeneous array, yes, because when you collect them all, then again you can put them into an array. In Java it doesn't work because one of the reasons why we have the composite pattern is, we can get a pen up here, is that we want to be able to say the following. Let's say that I have some kind of a function or some kind of a method that takes a component. So I might say add. Screen is messed up. It's not my day. I'll type it. Okay. Yeah. All right. So if I have some function add, and normally it takes a component, and then I want to be able to say add and actually give it a container. So if I make a like a JPanel, now that's a container. It's not a component, but I want to be able to say add p, and that only works if this in fact is a component. So it's essential that I can convert from the subtype from this type to the component type. And with arrays, that simply is not the case in Java. If you have like an int array that has 3, 4, 5, you can assign this to a variable of type int array, but there is no way in Java to say I want to have a generic array. There's no way of saying, no, give me an array. And so in that case, in Java, the composite pattern would not apply to arrays. In fact, it's not super easy to find examples in Java where the composite pattern does apply. You have it in the homework with those composite icons that are again movable icons, but that's kind of the same thing as with the containers and components. So that's not that different. We'll have another example later in the in the next section that's kind of revealing. All right, so composite is, think of containers, components and containers. Decorator. What's a poster child for decorator?
Scroll bars.
So to me, it's scroll bars because I know how the scroll pane works. So I've used it often enough in my life that I know a scroll pane can decorate anything. You may have never used the scroll pane, and so that might not be quite as convincing. And so the other example that's out there for the decorator is these decorations for readers, where you can take an input, any old reader, and turn it into a buffered reader, for example. Like I say, I don't think it's a very powerful example because there would have been easier ways of achieving the same effect, but it is a common example. So with the decorator, you're more interested in adding functionality, whereas in the in the composite pattern, you're more interested in collecting like objects. So it's a different focus. So here is an example of how to deal with this. In Swing, if you want to have a component such as this panel here, and you want to add a border to it, here is how you do it. You say, give me an etched border, and then you set the border of the component, and then you'll get this kind of etched effect here. There's also a titled border where you can specify a title, which is actually what I'm doing here. So that's how you make borders in Swing. You make the border, and then you call component set border. So it's decorative, right? What could be more decorative? Is it an example of the decorator pattern? So let's look at the decorator pattern. The decorator pattern says that we have some kind of an interface type. And we have the concrete components, the ones that want to be decorated, realize this interface type. Now, that's in Swing, they're not doing a great job with that because a J component is actually a superclass and not an interface, but I guess it could be an interface. And like a button or a panel, those are in fact subclasses of this, so that's good. Decorator classes also realize this interface type. And that's not something that we can use to make this decision. The decorator class here, that would be the border, right? I would guess. And so now the question is the border a component? Let's find out. Now let's go to the first one that I find. So border is in fact an interface, but when you look at it, it has no relationship with JComponent or component or any of those component classes. So this test fails. Border is not a component. So here you have something that's decorative, but it's not an example of the decorator pattern. And in fact, you can kind of see that's completely different. Every component in Swing knows how to apply a border because it has this set border method. That's different than with scroll bars. With scroll bars, there was no set scroll bars method. They could have engineered it like that, but they didn't. So interestingly enough, in Swing, the way that they apply borders does not use the decorator pattern, but for scroll bars, they did choose it like that. Why the difference? I don't know. It's easily imaginable to have the setup differently. One could have made it so that, say, that's just like you have a J scroll pane that has sitting inside it the component. You could have had like a bordered pane or something that has the border outside and the component inside. In fact, that's exactly what you're going to be doing in the homework, where there's going to be a bordered icon. Oh, I forgot I can't draw today. Okay. So where you have the icon sitting inside here, and then you have the border outside, and the whole thing is again an icon. That's how you're going to be rigging it in the homework. That is an example of the decorator pattern. So you can't say the borders are never an example. It always depends on how they implement it. Do we make it so that the border thing is again of the same kind as what's inside? Decorator pattern. Do we make it so that the border is an unrelated class that has nothing to do with the original hierarchy, and so that way we just have a method to turn it on or off? Then that's not an example of the decorator pattern. So here, this walks you through this this logic. Now, interestingly enough, if we look a little bit further, it's a little different here. There is a titled border, and let me show you that. So the titled border is the one that, where you can put a title like you had in this picture. And now notice what the titled border does. The titled border consumes any old border and produces a new border. That is the decorator pattern. So you can use a titled border to decorate any other border and give it a title. So weirdly enough, they chose the decorator pattern to have more complicated borders. You can have a titled border of an etched border, and that's a more decorative border. I mean, you can, and that's just what they did. And you can argue whether that's the best way. All right, so there will be, in the next midterm and in the final, because the design patterns are such an important part of the course, there will be questions that say, in this situation, does this design pattern apply, or which pattern applies? So it's important that you get good at making these tests. So the next example is designed to throw as many patterns as possible into a single application that has nothing to do with swing, so that we can see these patterns in a different way. So the idea here is that we want to have a description of invoices. Let's see if I have one somewhere. No. Okay, stupidly I didn't put an invoice here. So an invoice just has a bunch of line items where each line item has the description of whatever it is that you're buying and the price. So there is an interface line item here that you can see here. So a line item is anything that has a price and that has a description that can be written as a string. Then there is a class product that is a concrete implementation of this interface. So a product here has a particular description and a price, and then it has boring methods that yield the price and the description just like the way you would think. So that sounds like a lot of trouble for little gain. But now we're going to start spiffing up this example. So consider a bundle. So sometimes it happens that you want to bundle a bunch of things together and maybe sell them at a discount or something. So here, this is, as you can see, a very old example. These days, probably no one knows anymore what a stereo system and a tuner and an amplifier is, but now work with me here. So in the olden days, people built their own thing. Does anyone know what a CD player is? No, speakers we still have, but that's all right. So in the olden days, people built these audio systems from individual parts, and you could imagine that a store would sell some special where you buy them all together, and then the total price is cheaper. And so you can think of any number of bundles now. It could be like a laptop and a printer and a mouse or whatever. Doesn't matter. So you bundle these things together. Now think of how the invoice would look like. You would get the Pi Day bundle of the laptop and the printer and the mouse, and it would be on the invoice. It would say Pi Day bundle, and then inside it would probably say what the bundle consists of. Now a bundle has line items, right? It has the individual line items. A bundle is a line item because you want to be able to put it on an invoice. Which pattern? Well, it says right there, right? It's the composite pattern. So the bundle has line items, and a bundle is a line item. You could even have a bundle of bundles, right? Because a bundle doesn't know what goes on in it. It's just a line item. So here we have the code for that. So I like this example because the code is very simple. See, here's the bundle class. It has inside a list of line items. And now let's look at the methods. Let's look at the description first. The description makes a descriptive string of the bundle that starts out with the string bundle and then a comma delimited or comma separated set of the descriptions of each of the items. So it iterates over the items, and for each of the items gets the description, then it concatenates them all together. And that is super common for what the composite pattern does. In the composite pattern, one of the things that we hadn't talked about so much, but if you look at the pattern description, it'll say that to implement the methods of the composite, you will want to call the methods on the individual items and somehow combine the result. The same thing here is true for the price. This price here doesn't apply a discount. That's somewhere in the exercises. It simply adds the prices of the individual items. So now let's look at the homework. You have a composite in the homework that you have to do. Which one? Yes. I can't say often enough that it is not an effective idea to do these homeworks the day before they're due. There's no difference to the homework. The homework doesn't care whether you do it on Tuesday or on Saturday, right? Do it on Tuesday. I'm super serious. Do it on Tuesday, because then if the homework was so simple that you can do it in a day, then of course it doesn't really matter whether you do it on Tuesday or Sunday, right? So you might as well do it on Tuesday, because if the homework wasn't that simple, you can ask a question on Wednesday. It's just a shifting around of the things. So, and then on Wednesday, at least if you didn't get it done on Tuesday, fine, right? But at least you then have the basic lay of the land. The composite example in the homework is where you put multiple icons together. So, where you put multiple icons together. And then the whole thing becomes again an icon. So visually that's pretty simple, but now behaviorally, what does it mean? What are the methods on movable icons? See, you would know this if you had completed. The methods on movable icon are draw, move, and get bounds. So what is draw going to do on the composite icon? How are you going to implement it? Exactly. It's going to call draw. It's exactly going to be this loop here, except these things are going to be renamed, and it's going to call draw. How about move? Same thing, right? Movements. It's going to be a loop that moves them. How about get bounds? Yeah, so it has to call get bounds on each of them, and then it has to find out the rectangle that contains them all. As it turns out, there's a nifty method in Java AWT rectangle that when given two rectangles, it gives you the one that has both. Union. So union is a little inaccurate. It's not the set theoretical union, because it also contains these things here on the side. It is the smallest rectangle containing them both. So in other words, the code for get bounds is going to look almost like this one here, except you don't really add them up, but you add them up using the union method. You can in fact start out with an empty, I'm not totally sure. You may not be able to start out with an empty rectangle. Because the empty rectangle would sit up here, and then that would always be included. So what you have to do is you have to set the result to the first bound, and then you go and add on the second, third, fourth, and fifth bound, and so on. But that's just a technicality. So and this is super characteristic of the composite pattern, that in the composite pattern, all of the various interface methods that you need to implement, because after all, the composite should implement the same interface as the individual components. All of those they just loop over the individual components and somehow combine the results. Now here we're combining strings, here we're combining numbers, you're going to be combining rectangles, and withdraw and move, you're just going to be combining actions. Yes?
When we implement the get bounds in the compound shape, we're supposed to get the max and bounds for all the equations?
Well, yes, but that's what you have to compute. But what I'm telling you is that what you can actually do is something slightly simpler. You can call get bounds on the first one. And then for all the others, you call the individual get bounds. Then you form the union with the previous one that you already have. The union will give you the next bigger rectangle. And then you form the union one more time, and then that's going to give you that rectangle. If you don't like that, you can certainly follow your approach and take the minimum of all of the x's, the maximum of all of the x's, the same with the y's, and then form a new rectangle out of it. I like my way because it so closely mimics what you're doing here, right? Instead of adding something up, we're kind of adding these rectangles where the notion of adding means to take the union. But either way will certainly work. So the point is that in the composite pattern, what you do, you always do this kind of combination thing. Okay? And so this code here is the poster chart for composite. You collect the individual items, and you have a bunch of methods that loop over the individual items. Your composite shape is going to look exactly the same way. And so then here is the UML diagram. And so here I've translated the UML diagram from the general situation to the bundle. So you can see a bundle is a line item. And a bundle has multiple line items. That's what the star means. You can then also see there's a get price function in here. There's a get price method in here. And the comment says it calls it for each one, each of them, and combines the results. That's what's so characteristic. All right, next. Discounts. So stores can give discounts, and we're going to be using the decorator pattern for discounts. So we're going to be saying, there is a discounted bottle of rum. So there's a product, a bottle of rum, and then the discounted one is derived from that. And so let's look at the implementation here. Super simple. We're storing the item that's being discounted and the discount rate. The computation for the toString, it gives the original toString and then it shows what the discount. The computation of the price, it just does the percentage calculation to apply the discount. So what's the difference between the composite pattern and the decorator pattern? On the implementation, not much. The main difference is you only have one thing inside here instead of a collection of things. And in the implementation of each of the methods, then you refer to the equivalent method on that one thing as opposed to be on all of them. Now that tells you that you pretty much now know how to implement the bordered icon. So one of the homeworks is you have some icon, and now you're supposed to make a bordered icon that has a border around this thing. How many methods do you have to implement? For it to be a movable shape.
All the methods from icon?
All the methods from movable icon, yeah. What are those?
Draw, move, get bounds.
Thank you. Draw, move, and get bounds. Okay? So how are you going to implement draw? So kind of think about what are you going to have? You're going to have a bordered movable icon or whatever the thing was called, and it's going to have the original icon inside here. And so in a method, you're going to call the equivalent method on the thing inside, and then apply the decoration. So how are you going to do draw?
Call draw on whatever.
Yeah, you're going to call draw on the thing inside,
And then draw on your board.
and then somehow you need to draw the board. That's how draw is going to. How are you going to call move? You surely will call move on this thing. And now it depends on your implementation. If you actually have an instance variable for the border, for this rectangle, you also need to move the rectangle. If you compute that rectangle on demand, then you don't need to do it. How are you going to call get bounds? You call it on the inside, and unfortunately you may have to adjust it, because if there's a gap, then you're going to have to adjust by the gap. As a tip, if you are in that situation, so if you get the bounds from the inside, you can call, there's a method called grow that you can call to make it a little bit bigger. Then you don't have to compute it by hand, or you can compute it by hand. So that's the decorator pattern. And so again, this is a very characteristic code example to follow, because you see the thing that is being decorated and the various methods. Yes? What's that? Well, the way it's specified in the homework is to say you construct a titled, a boxed or bordered or whatever it was called, by giving the shape that's inside and a measure of a gap that can be 0 if there is no gap, or it could be some non-zero number. And there's in fact one example where it has a gap of 0 and a gap of 5. And then, so where you have one of these things inside another bordered one inside the original one, and then the gaps become important. So that's just a minor technical issue to deal with those gaps. So here's, again, this very similar looking diagram where you can see a discounted item has a line item and it is the line item. So there is, let's see, in the interest of time, do I want to go into this? Yes, I will. All right. So there is a GUI display to this whole thing, a completely gratuitous GUI, but it shows a common thing that when you want to have something that views a data structure, in this case our data structure would be the invoice, and if you add things if you change the data structure in any way, then you want it so that anyone, in this case the code that's viewing the invoice, can be notified when a change happens. So in other words, you want to implement a change listener mechanism. And so in this case here, I'll just show you how it's done. So what we want to be able to do is we're going to take the regular old change listener that's used in sliders, just because I didn't want to reinvent the interface. And the invoice class is now going to implement the change listener mechanism, just like the slider does. Normally, when you're a consumer of this mechanism, when you use Swing and you just want to be notified when a slider is moved or when a button is clicked, you don't care about how that mechanism is implemented, but it is useful to know how to implement it. And so the way it works is that the thing that is willing to do the notification, the subject in the terms of the pattern, has a collection of all of the listeners inside. And then whenever something changes, then it tells them all. So the way that's done is you make a new change event, and then you simply get all of those listener objects that you have collected, and then you call whatever the method in that functional interface is, and it happens to be called state change for change listeners. And you just fire this message on all of your listeners. So the way this is then done from the consumer part this is in the GUI code that what I'm not going to look at today, is that we have the invoice and we have a text area, and now the invoice is rigged so that whenever the invoice changes in any way, then the text area is going to repaint itself. That way the invoice class doesn't have to worry about how anything gets repainted. And that's good because the invoice class knows nothing about user interfaces. So this is a very good way of decoupling any kind of a GUI situation from a class that holds a complex state. And something that you will often find yourself doing, that if you have something that's dynamically visualized, that you add a change listener like that. And it's the simplest thing in the world, that whenever a change happens, you just fire up to anyone who was interested by implementing this loop. So there also needs to be a method to add listeners. Let's see where I find that. No, I don't have the code here. But when you go through the code, you'll see there is a method to add listeners. It simply tosses it into this list of listeners. You could have a method that removes listeners. I don't think I have that, but it would be cheap thrill. You would just remove it. So in the end, and I'm not going to cover that today, it talks about how to iterate through the invoice. And so the idea here is that that an invoice has line items. One needs to if you want to do something with the invoice, you need to be able to see the line items. Now, one way of doing that would be for the invoice class to give out an array list of all of the line items. And you don't really want to do that. That violates the law of Demeter, if you remember. You don't want to give a reference to your liver. And I guess one could give a copy of the array list, but that's potentially expensive. What if someone only wants to look at the first item? So giving an iterator is potentially a reasonable way of doing it. The other reason that giving out an iterator is a good idea is, in this example, what's an invoice? It's just a Java data structure. It's an array list of line items and maybe like an address or something, I don't remember. But it often happens that you don't really store all of this data in Java objects. If you have 1 million invoices, you probably do not have 1 million Java data structures. All of those invoices are stored in a database. And so you might want to do it so that you do direct read and write from the database or from some intermediate cached object or something. And in that case, you might not even have the array list. And that would be cruel if you had to assemble it. Giving out an iterator is something that you can always do fairly easily. So that's the idea of saying that it's often a good idea to give out a data structure that iterates. Now, in 2017, whether the Java util iterator is the right data structure is a different question. So that's why I don't want to belabor this example here too much. All right, so the important part of this example and why it's worth your time to look at it is really the implementation of the composite and of the decorator, because that might help you with the homework. So if you need some extra code examples, keep this in mind. So the other thing that I want to do today is pick up on, and that's why I didn't have any quiz at the end, because I know this is going to be time consuming, pick up on what we talked last time about how to better decipher books. So I've put together this little set of lab questions here. So let's go to the slides. So do this with a buddy. Can be a different buddy. Look at this section of your textbook. And that's the section that I put up last time that has the little sequence diagram. Then look at the code of Chapter 2 Mail, that mail program. And I want to know exactly which line of code corresponds to this figure. And then I want you to fill in some details in this diagram. And I want you to tell me, and we talked about this last time, if you have a call x.f of y, and now you have an arrow that does f, what are the types to the left and to the right? And look at this example for guidance. And then we'll go through the same thing with with a create arrow, which corresponds to a constructor call like that. And then we'll all talk about this together. Then I want you to carefully read through a description of how lambdas work, because I think that's another thing that why probably this exam question was confusing, is there's one sentence that exactly explains how lambdas work, and I don't think that everyone has that internalized. So I'd be interested in seeing how that goes. And so then we're going to translate that thing into a sequence diagram, and then we'll work through the exam. So I'd like you to spend with each other 15 minutes or so on the first two, and then depending on how we're doing on time, I might just do the third one standing in front, and we'll all do it together. But it is important to me that you do this and talk it through with a buddy. Okay? So with this one, definitely no single fighters. I want you to just chat this through. All right. A mailbox. Add. What are we adding? Message queue. Who are you working with? You need someone.
Okay.
There's 3 people in the back.
Okay.
Walk up to one of them.
Sure.
The native one is called Preview.
Nobody uses why. It's like coding.
There's no line. The line is not yeah, there's no message.
Yeah, I have that class.
We have an arrow lane there somewhere. So that part now my question is, no, that doesn't
X86.
So my question is, where is X? Tell me where what is the equivalent of
I know, you have to go up.
Up there.
What is this?
Should be that. No. Yeah, so I think I'd have to like 3 of them or something.
Shit.
Can figure out how to do that. And also moving backward. Command tab on that, but it's Alt tab on a PC and the Alt controller switch. So it, I can do it as a mechanics and yeah, but then when you're in Chrome, tab is control tab.
Yeah.
For me, for in a PC, it was the other way around. Yeah, so it was like this Alt is here, and then
Fingers are going the wrong place.
So when looking at this thing here, which class does add belong to?
The message queue.
So, you know, it's either mailbox or message queue, right? And so in mailbox there actually is no add method, but there is one in message queue. And if you now want to find where it was called, there's a nifty feature in Eclipse that I'm sure IntelliJ and NetBeans also have, where you do references workspace. And now it gives you all of the places in the workspace where this particular method was called. So this is much better than doing a text search, because if there are 5 methods called add, then the IDE can tell them apart. So here it says an add message and a save current message. So here is one. And is that the one? Yeah. So so this is in the mailbox class, and I guess this is exactly the one that I was after. Why don't you see the a message?
The sequence diagrams don't have that.
Yes, you can never see parameters, as the book points out somewhere. When drawing a sequence diagram, you omit a large portion of detail. Generally, you do not show branches. Does it say about parameters? Maybe it should say about parameters.
I think it's up to that part.
Oh, it said somewhere, right? I could swear I wrote
It
this.
does say something about
I could swear I saw this.
it. You cannot tell from the diagram right after the code.
Ah. Okay, so in the sequence diagrams, you can never see parameters. They're just invisible in the diagram. Yeah. So anyway, I just wanted to point out the nifty feature in Eclipse in case you ever needed to find references. Yes.
What did you get?
Not that I checked it.
Oh, you haven't checked.
That's all you would want to Xcode. Yeah.
We'll get the only part I don't understand is this.
We'll get to that. We go to move on to part 2 of the lab. And I should have done this one. The system is fine. Oh my god. Next up, yeah, so this is one way to there's no way that's no, that's the one that's being called. Oh, okay. That's what I just did by doing clips. Yeah. Okay. So that's the one that you want to add. Okay.
Why did you? What do you think happens? We put this on the test. Put this right here, and then it shows up like this. See, you can do just create. Or like I ended up doing this, but I still got more code.
All right, so let's get everyone on the same page with the first part so that I get you into the second part. So it says here, which line of code corresponds to, and we just talked about which line of code that was. There was this line of code. And so the important part now is, in general, if you have a call that x.f of y, and so now we need to draw this diagram. Well, we know this arrow must be labeled F. Where's X?
Right.
Okay, who votes for the left? Okay, no one votes for the left. Good. The X is over here, right? So you would write X and then its type, which we know to be C. Okay. What is over here?
Question marks.
Well, it's whatever the code is that contains this line. So if this one here was inside a class W and some method void M, then it would be something of type W. And we don't know what it is. That depends on the context. And so we don't really know in the sequence diagram. It is super important that you realize that the thing that is being called is to the right. So you know, if you look at this piece here means X to N. A lot of people, I don't think, were clear about that part in the exam, because I just, when I grade it, I just look at these arrows, right? And I say, is in fact F called on whatever is here called on whatever is on there? And if not, what choice do I have? I mean, that's so that's the basic notation here. And it is a great notation. It is what it is. All right. So and now with the constructor calls the same thing. So let's look at how you draw this. So x is nu a with some parameters. At this point, you've caught on to the fact that the parameters don't show up. How do you draw it? So in the book, it talks about these create arrows, and obviously it must have something to do with it, right? So here's a create arrow. What do you notice? What's different about the create arrow? Like, what's completely different about it than about the other arrow? Yes. Okay, yeah, the funky brackets, yes, but more importantly, it points to the object that's initialized. It doesn't point to one of these timeline things. Okay? It's different. That's the notation. It points to that, and so you do have to follow the notation. So we know that there's going to be an arrow called create. We know it's going to point to some box. Do we know the type of that box? So we know it's of type A, right? Because we're making a new A. If there's any one time that we really know the type, it is after new. Okay, do we know its name? Do we know its name? X, because it's soon going to be saved in X. The Y is a parameter, it doesn't show. Okay? So that's all we know. We know there's some bar here. We don't really know from which context this comes. Whatever the code is that contains this line. So it's super important that when you draw a create arrow, that you really do draw it like that. Otherwise, it makes no sense. It doesn't make sense to create something that already exists. Yes?
So on the slide, you say X is of type C. Is that a typo?
I must have meant a different X. Oh, yes, that's a typo. Thank you. Yes, that is a typo, because it doesn't make sense, right? X can't be both of type C and of type A. Or maybe C is a supertype of A.
Yeah,
okay, fine, yeah, maybe it's a supertype, yeah.
But if it's a supertype, then it should say X colon C.
No, you want it, it's an object. These things are all objects. Actually, I should technically underline them because in UML objects are underlined. And with an object, you always want to give the exact type. It's not the type of the variable that you're after, but the type of the object. And that's why later we go to these contortions and say, we don't know what the exact type is, but it implements whatever. Yes?
Now, I was trying to do underlines in the UML. I didn't allow it.
Yeah.
It didn't allow it.
It does. You just have to carefully drag it to the top node.
Underline like inside the text box.
The tune is very confusing.
Say again?
No, underline like that. So if it's like a...
It doesn't underline?
It doesn't, because in the timeline it says, oh, you can use HTML text, right? And I put HTML.
No, you shouldn't have to do that.
Okay.
I thought I underlined. It's been a long time.
UI, I used the UI. I don't know if that exists.
So, file, new sequence diagram. That underlines. Here. Yeah, so let's do that. So the way you draw it in Violet is you drag it inside here, and bingo, it even makes a create arrow. Okay, very intuitive.
There should be a separate lecture for how we use this gift. Just one section dedicated.
Yeah, well, no one forces you to use it, right? You can just use whatever one you like. All right, so that's that. Now we're running really short on time here, so I'm going to do this today. Yeah, let's at least go through the first step, and then we'll pick that up next. So I want you to look at chapter 5. And I want everyone to read, where the heck is it? Just here. that one sentence in section 4.5, the first few sentences. And just draw that sequence diagram, then we talk about it, and then we do the rest later. Yes. 4.5, what the heck am I doing? Chapter 4. All right, so everyone's read the sentence here where it says, this statement has the same effect as constructing a class implementing comparator, defining the compare method of that class, and constructing an instance. So here it says compare country comp equals, and now it says the thing here actually constructs an instance of a class. So how are we going to draw it in UML? What kind of an arrow do you use when you construct an instance of a class? You have to draw a create arrow, right? There's no choice. So it's create. There's some timeline over here. And so we're creating an object of some class. What's the name of the object? Com. Just like last time. This thing here on the left. It will soon be called com. What is its type? Yeah, so you would first of all say probably comparator of string, the string country, a country. And so technically, we'll write question mark implements because we don't know the exact type. That's the type. So that's how you draw this line here. What about compare to? Why aren't we drawing compare to?
Because that's the compare method, but the method hasn't been called.
Very good, because it has not been called. Right? Compare to will be called later, much later. But right now it hasn't been called at all. And that's the beauty of a sequence diagram. It shows exactly that it hasn't been called. Okay? Yes? Yes, so what actually now happens, probably this code will call some kind of a sort somewhere, and then that thing will call compare. Now, that'll actually call compare. So there's another trickiness here. It will not call compare to. How can you even see that it calls compare?
It's the only method of the.
Yeah, and so it is a super compact notation. Compare is the only method in comparator. So you can't even tell that from this piece of code. You have to look at what comparator is. Comparator has one abstract method, and it's called compare. So over here, this code will call compare. And now you could say, well, are we ever going to see this call to compare to? Probably not, because that's for which method here is compare to belong to? String, yes. And you don't normally show what goes on with mundane things like strings. Yeah. You could, at this point here, maybe want to show the countries and to call to get name, right? So presumably this here now calls get name and on two countries. And I don't know, one might want to show. Okay? But again, the line that belongs to just that top line, the diagram that just belongs to the top line was nothing more than this. So we're going to continue this on Monday with decoding the thing in the exam, but you might want to give it a good try on your own, and I think seeing this will help you a great deal. Okay? Any other questions? Put them on piazza. Thank you. And if anyone happens to draw these, write these down, you could put them on piazza too. That'd be nice.